This video presentation covers the design, construction, and flight of the Spirit of Knoxville, presented by the Wingineers of the University of Tennessee, Knoxville. This is the 3-view drawing submitted in the report showing the overall dimensions of the Spirit of Knoxville. Since the report submission, some slight modifications have been made, which will be shown on an updated 3-view on the next slide. As shown, the overall length of the airplane was 71 inches. The wingspan was 60 inches, and the fuselage width was 6.625 inches. As mentioned earlier, the design was modified slightly after the report was submitted, but the primary modifications were in the tail area. First, the portion of the fuselage where the stabilizer is mounted was made rectangular rather than tapered, so that the angle of incidence could be set more easily during construction. The stabilizers themselves remained unchanged. The second change was made to the deployment system, in this region, in front of the tail and behind the sensor simulators. To connect the fuselage to the rectangular portion of the tail, the fuselage taper was adjusted in both the vertical and the span-wise directions. This table shows the gross weight of the airplane along with the location of its neutral point and center of gravity in each of the 3 mission configurations. The static margin was reasonable for the Mission 3 configuration, but the Mission 1 configuration turned out to be too nose-heavy, so lead shot was added to the tail for Mission 1 so that its static margin turned out to be the same as the one for Mission 3. This way, the pilot did not have to adjust to drastically different stability characteristics for each mission. The control systems for the airplane are powered by Bluebird BMS A930 metal gear servos. The left and right ailerons are at the top of the screen, with the stabilizer control surfaces shown on the bottom left. The receiver and flight controller connections are shown in the bottom right. Shown here is a demonstration of the control system. First is a demonstration of aileron movement, followed by elevator control, and rudder movement. The Multrafly DM5320 brushless motor was chosen for all missions. This motor was rated for 8S LiPo batteries with a maximum power of 2700 watts. The Phoenix Edge HV120 electronic speed controller was selected because of its maximum current capability of 120 amps, which was more than the maximum allowable current for the motor, 91.22 amps, and thus prevented overheating. Based on our calculations, a 19-inch by 10-inch propeller would produce the ideal performance for all 3 missions. To make this design, the team began with a sensitivity study of the variables applicable to the deployable sensor. The plot shown here was generated in MATLAB by holding 3 of the 4 variables constant and changing the 4th variable to determine which of the 4 had the greatest impact on the score. This showed us that an increase in the sensor length would boost the score more than an increase in the other variables. However, to increase the length of the sensors, something else would need to decrease. The plot shows that decreasing the sensor weight would reduce the score the least, and thus we decided to make the sensors as long and as light as possible. These photos show the final design of the towed sensor. With a body diameter of 1.65 inches and an overall length of 10.5 inches, the total weight of the sensor was roughly 7.6 ounces. The circuit was powered by 2 9-volt batteries and controlled by an Arduino Nano, and was used to create a blinking pattern on 3 10-watt LEDs. A tow cable with the necessary signal and ground wires were fed through a hole on the opposite side of the sensor body. Jewelry clips were used to make the sensor easily detachable from the aircraft, while the male wires protruding from the sensor corresponded to female connectors on the aircraft. To predict mission performance, we compared the power required to the power available to estimate cruise speed, providing an estimate of the time required to complete each mission. Combining this with knowledge of battery consumption, we determined the number of laps we'd be able to complete for each mission. Based on this number of laps, we estimated our raw score for each mission. Each shipping container was made of cardboard, with packing tape to secure the seams. In the report, the square face of each container was reported as 3 inches by 3 inches, but this was reduced to 2.5 inches by 2.5 inches to make the loading process easier for Mission 2. On the left is a picture of 4 of the sensor containers loaded into the cargo bay of the fuselage. The other 4 sensor containers sit directly on top of these in the same orientation. On the right is a video of the sensor containers being loaded into the final design of our airplane. Simply remove the hatches at the top and load the containers directly into the cargo bay. To unload them, just reverse this process. This slide shows an inspection of the plane from multiple angles. First, the plane is shown from a top view before being shown from the front. Then the plane is shown from the back, and then the side. This inspection shows how the airplane matches the design plane, as shown in the 3 view. This video clip shows the operation of the deployment system. As shown, both doors are connected to the same input. Once the doors are opened, a second input is used to rotate a continuous servo which rotates a winch. A flag marks the 5-foot mark on the cable, but for now that is pulled up so that the sensor remains suspended above the ground. Once the sensor is deployed, a third switch turns on the sensor lights. This process is then reversed to prepare for landing. The stability of the sensor in flight will keep it from twisting like this.